Anyways. Thank you. Right. Thank you, Claire, so much. So hi, everyone. Thank you so much for attending my talk today. Again, my name is Cassie, and I'm a PhD student in the anthropology department at Purdue University. I'm here to talk to you about the research that I completed over the past 2 years on a very small portion of the metalworking debris that is excavated from Fort Ouiatenon, which I plan to expand upon as I continue throughout my degree. So I'll first start off my presentation by providing a brief overview of the history of the French occupation at Fort Ouiatenon. As the first French colonial settlement in Indiana, established in 1717, Fort Ouiatenon was a crucial early site in the relationship between colonial and indigenous lifeways during its occupation. Fort Ouiatenon was established through negotiations between the Ouiat, a powerful band of the Miami tribe, which had a large settlement across the river, as well as the Kickapoo and Mascoutin tribes, which had villages around the fort area, and the French colonial government. After the establishment of Fort Ouiatenon, trade heavily increased between these groups in this region. At Fort Ouiatenon, relationships between the French and colonists and indigenous groups grew hostile during the late 1740s, as the British began encroaching into the Midwest and trading goods at lower prices to attract new partnerships from indigenous groups that were previously aligned with the French. When the truce between France and Britain ended in 1744, British colonists began to trade with the French indigenous allies as British goods were exchanged at a less expensive rate. Turmoil between the French, British, and various indigenous powers increased again in 1756 with the beginning of the French and Indian War. Indigenous and colonial dynamics within the Midwest revolved around the sources of trade goods and allyship established through trade networks. As the French relied on indigenous support to run their forts and support their trade networks, the waning support of the previous indigenous allies was harmful to French interests. Ultimately, conflict within the region led to the British takeover and occupation in 1760. Fort Ouiatenon resulted again in negotiations between the French and the Miami, Kickapoo, and Mascoutin villages living in the area. These negotiations took several rounds, with the Miami ultimately granting permission to the French to construct the fort on the opposite side of the river from their community, with the promise that a blacksmith, French official, and missionary would reside there after its completion. Indigenous allies like the Miami made demands and requests of the colonial powers in return for their support of these French forts. At the time, the Miami wanted a trading post closer to their territory to avoid traveling long distances through potentially dangerous enemy territory to trade their furs at French forts in Detroit. The completion of this request by the French would demonstrate their commitment to the Miami, as well as the commitment of the French colonial government. This demonstration of commitment solidified the appearance of power and sovereignty of the Miami in the Midwest to their potential enemies and allies. According to historical French accounts, about 20 French fur traders and their family lived at Fort Ouiatenon by 1746, along with around 600 Ouiat warriors. Based on the historical records from other French forts in the Midwest, a blacksmith lived at the fort during its occupation and was presumed to perform a variety of tasks associated with making and repairing metal, trade goods, and weapons. French colonial blacksmithing is currently an important phenomenon that is currently understudied and underrepresented in current literature. This research provides a preliminary assessment of what kinds of activities occurred at Fort Ouiatenon based on the analysis of metallurgical waste. The blacksmith was one of the most essential tradesmen of any fort. They were a one-stop shop for most any item made from metal. They made household items such as pots, pans, and sewing needles. If you needed tools, they made hammers, nails, axes, shovels, as well as weapons and more. Typically, a blacksmith spent most of his time repairing items unless they were a master craftsman who specialized in certain items. Blacksmiths were an essential part of both indigenous and colonial lifeways, as demonstrated by the request of the Ouiat. Blacksmiths repaired metal goods and weapons, which was a valuable service for indigenous groups. Blacksmiths crafted and repaired everyday goods, which were essential to the daily operations of the fort. Blacksmiths at other French forts, like Fort St. Joseph in Michigan, were generalists and had skills to repair many iron objects, though most of their time was spent repairing indigenous weapons. Gun repair benefited indigenous communities, especially when defending their territory from enemy powers. Indigenous tribes used guns when hunting and waging war on enemy nations. Strategic, economic, and political bonds were strengthened between the French and their indigenous allies through the presence of a blacksmith and the repair and production of metal goods at French outposts. This research I conducted investigated metallurgy and blacksmithing within the context of the French fur trade. More specifically, this research focused on examining the blacksmith's role in daily operations at Fort Ouiatenon and economic activity within the region by analyzing evidence of a component of the metals manufacturing process at the fort. Due to the demand from indigenous communities for metal goods and the repair of firearms, blacksmiths played a crucial role in the cross-cultural interactions between these indigenous groups and colonists involved in the fur trade. Using artifacts excavated from Fort Ouiatenon during Michigan State University's excavations in the 1970s, I aimed to address the following research questions. My first question was whether the material previously identified by researchers from Michigan State University as slag related to metallurgy or other pyrotechnic activities, meaning activities that require the use of fire and high temperatures to produce an object at Fort Ouiatenon. My second research question was, since there are different kinds of slag, does the material in the study represent blacksmithing activities or the smelting of ore? My final question was, does this material represent a metalworking area or a blacksmith disposal area? For this project, I examined a selection of waste artifacts excavated from Fort Ouiatenon in the 1970s. Over 100 kilograms of presumably metallurgical waste, commonly called slag, was excavated from the fort during this time. Studying the metallurgical waste from Fort Ouiatenon aimed to understand French colonial metallurgical practices, as well as colonial metal production and shared technical traditions within the French fur trade in the Midwest and Great Lakes region during the 18th century. My research addresses more critical questions surrounding French frontier colonial metalworking traditions and adaptations during the 18th century, and specific questions about the blacksmith activities at Fort Ouiatenon. So I'll then start off with talking about some of the history of excavations at the fort, with the first excavations at Fort Ouiatenon occurring in the summer of 1968, led by James Keller from Indiana University, Bloomington. After the discovery of Fort Ouiatenon, the Tippecanoe County Historical Association requested Keller to begin excavations at the fort. Little is known about the 1968 and 1969 excavation seasons led by Keller, as this work was never formally published. Currently, field notes from the 1968 and 1969 excavations are held in the Indiana University Museum of Archaeology and Anthropology. Later excavations, led by doctoral students Virgil Noble and Judith Tordoff at Michigan State University in the 1970s, furthered what was known about the fort, including the location of a possible blacksmith forge. All field notes and documents from the MSU excavations are located at the Tippecanoe County Historical Association. Virgil Noble was the first person to employ a systematic sampling of the fort from 1977 to 1979. Noble attempted to piece together Keller's previous excavation work and set out to survey the site and identify the bounds of the fort. Through his survey methods, Noble inferred site activity and occupation based on the presence and proximity of different classifications of artifacts, as well as the identification of multiple activity areas of the fort. Tordoff examined faunal remains to infer subsistence strategies at the fort. Analysis of faunal remains identified an extensive reliance on locally caught animals for subsistence, supplemented with domesticated animals. Fort Ouiatenon was considered to be a local trading center compared to larger regional trading centers in the Midwest, like Fort Michilimackinac, which had a larger distribution network. As a local distribution center, Fort Ouiatenon was deeply embedded within the region's indigenous activities as it relied on local resources. Tordoff also sent out to identify the location of a possible blacksmith forge. Tordoff focused on investigating the portion of the fort suspected to be a blacksmith workshop based on the presence of metallurgical waste recovered from in and around that area. The boundaries of a possible forge area and three refuse pits feature areas were located and identified as the blacksmithing forge active during the fort's occupation based on the presence of different artifacts associated with metal production. The samples analyzed in this research were excavated from Feature 35 in Excavation Unit North 995, West 905, on the left of your screen, described as Tordoff as a defined circular pit. This pit feature had a mixture of mottled gray clay, sand, and charcoal. This pit also had a ring of iron oxide stained soil and a ring of burned clay containing ash. A large quantity of metal artifacts and metallurgical waste was excavated from this feature area. Artifacts from this feature area included a straight pin, French gun lock plate, gun parts, a pot hook, an iron bucket, inlet, an axe fragment, a chain link, sprue, brass scrap, and brass rods. Based on this artifact distribution, Tordoff concluded that Feature 35 was a forging area refuse pit utilized during French occupation. Tordoff also identified feature areas 36 and 37 within that unit, which are the other two dark soil areas in the image on the left of your screen, as both French forge refuse pits that had similar artifact distributions. Archaeometallurgy is the interdisciplinary field that combines principles from archaeology and metallurgy to study past metals and material working technologies. Essentially, it's the science of understanding how people in the past made and used metal objects, from simple tools and weapons to elaborate jewelry and artifacts. This field not only examines the physical properties and chemical compositions of metal artifacts, but also explores the historical, cultural, and technological context in which these items were produced and utilized. At its core, archaeometallurgy seeks to answer questions about the origins and development of metallurgy, the techniques and processes of past metal workers employed, the sources of raw materials, and the role of metal objects in past societies. It involves excavating metal artifacts from archaeological sites, analyzing them in laboratories using advanced techniques, and reconstructing past smelting, casting, and forging methods. This study investigates the metallurgical activities of Fort Ouiatenon by analyzing pyrotechnical debris, often called slag or clinkers. Slag is a combination of silica and various oxides produced by different pyrotechnical processes that require the use of high temperatures, which includes metallurgy. Archaeometallurgy employs analytical methods to understand past mining, manufacturing, and the consumption of metals. Archaeometallurgy can contribute to the study of social and economic factors that influence metal production and use in past societies. Identification of archaeometallurgical waste must be made through a combination of methods. It is challenging to distinguish between smelting and smithing slag, which are both produced during metalworking processes with just our eyes, as they appear to be very similar. Smelting is the process used to extract a metal from its ore, which is the raw material or mineral in which metals are obtained. Ores are usually compounds of metal with other elements. The goal of smelting is to separate the desired metal from these other elements so it can be used to make products. Smelting begins as the ore is heated to a very high temperature in a furnace. The temperature needed depends on the specific metal being extracted, but it's usually extremely hot, well beyond what a regular fire can provide. This is because the bonds that hold the metal atoms together with other elements in the ore need to be broken down, and high heat is the only way to do this. Along with heat, a substance called a reducing agent is often added to the furnace. This agent helps to remove oxygen from the ore, which is a process called reduction that leaves behind the pure metal. For example, in iron smelting, carbon is a common reducing agent. It combines with the oxygen in the iron ore, leaving behind liquid iron that can be molded and used. Inside the furnace, several chemical reactions happen between the ore, heat, and the reducing agent. The reactions are what break down the ore and free the metal. Once metal is freed from the ore, it usually melts and collects at the bottom of the furnace because it's denser than the slag, which is in this process the leftover material from the ore and the reducing agent. The molten metal can be drawn off and cooled to form solid metal, while the slag is removed, discarded, or used in another process. Blacksmithing, which differs from this, involves shaping and manipulating metal to create objects. There is no extracting metal from the ore, as you are already starting with a metal product. The process typically involves heating metal in a forge until it becomes malleable, and then using tools like hammers, anvils, and tongs to bend, cut, and shape the heated metal into the desired form. The first step in blacksmithing is to heat the metal. This is usually done in a forge, which is a type of fireplace or furnace designed to produce the high temperatures needed to make the metal soft enough to work with. The forge uses fuel, traditionally coal or charcoal, to generate heat. Metals like iron or steel are commonly used because they can be heated to a point where they are not malleable without melting. Once the metal is hot and malleable, the blacksmith uses various tools to shape it. The anvil serves as a solid surface against which the metal can be hammered and shaped. Hammers of various sizes and shapes are used to bend, flatten, and stretch the metal into the desired shape. Tongs are used to hold and manipulate the hot metal safely. Blacksmiths can also join pieces of metal together, a process known as forging welds. This involves heating two pieces of metal to a very high temperature and then hammering them together so that they fuse into one piece. After the metal has been shaped and any necessary components have been joined, the blacksmith finishes the product and removes it from the heat. Iron smithing slabs are made up of oxidized iron flakes that broke off of the iron object being worked due to the hammering and heating, and mixed with the contaminants like fuel ash, flux, ground surface sediment, and the lining of the furnace where the smithing occurred. Highly glassy slag and the presence of charcoal and charcoal imprints within the slag often indicates smelting or smithing activity at an archaeological site. Smelting slags usually have a glassy, pumice-like exterior because of the reactions between the fuel ash and silica in the furnace walls. However, some smithing slags may also exhibit this visual characteristic. The chemical element manganese is present at higher concentrations in most smelting slags, but is identified in lower concentrations in smithing slags. Due to the rapid cooling process, the metal microstructures in smelting slags often consist of long crystals and fine dendrites. In contrast, metal microstructures in smithing slag usually consist of equal-length crystals and blob-like microstructures. The use of visual analysis, chemical analysis, and microstructural analysis, combined with any contextual information from the site, must be used to differentiate between evidence for smithing or smelting activities. For this project, 20 waste artifacts excavated from the fort were selected for analysis. The 20 metallurgical waste artifacts sampled from this project were randomly chosen from a box within the Tippecanoe County Historical Association collections, which in total contained about 530 waste artifacts, all from Feature 35. 3.7% of the artifacts were sampled from this box. The sampled artifacts were photographed, and each sample's weight, length, and gauge were measured and recorded. So for the methods that I used, the first one was portable X-ray fluorescence, also known as PXRF. Portable X-ray fluorescence is a non-destructive analytical technique used to determine the elemental composition of materials. Imagine it as a high-tech handheld gadget that can instantly tell you which elements are present in any object it scans, from metals and minerals to paintings and archaeological artifacts. When the PXRF machine is first pointed at an object and activated, it emits a beam of X-rays towards the object. These X-rays interact with the atoms in the object. The interaction causes the atoms in the object to emit secondary X-rays, a process known as fluorescence. Each element in the periodic table emits X-rays at a unique energy or wavelength when excited. The device detects these emitted X-rays and analyzes their energies. Since each element has a unique signature of specific energy levels, the device can identify which elements are present based on the energies of the X-ray that it detects. The results tell you which elemental composition of the artifact is. This can include a wide range of elements, from common ones like iron and copper to trace elements that appear in small amounts. PXRF is a useful tool for analysis of metallurgical waste artifacts for multiple reasons. First, PXRF is non-destructive. It's ideal for examining valuable artifacts, artworks, or any material where preservation is key. Its handheld nature allows researchers and professionals to use it in the field, proving immediate analysis of results on site, which is valuable for archaeology. PXRF can also analyze a wide variety of materials, including metals, ceramics, soils, and even liquids. This versatility makes it a go-to tool across many disciplines. Compared to traditional lab-based analysis, PXRF provides a more accessible and cost-effective way to obtain elemental compositional data without the need for sample preparation or destruction. The samples in the study were analyzed using a Bruker Tracer 3 SD portable X-ray fluorescence machine with a rhodium target X-ray tube and silicon drift detector to determine the chemical composition of each sample. Metallography is the analysis of the physical structure of an object at a microscopic level. The identification of different structures within a metal waste artifact can provide information on the type of artifact that was produced, as well as how it was produced, as different metal microstructures indicate different modes of production or only appear in certain types of metallurgical waste. The first step of metallography is to take a small piece of the sample and prepare it for examination. This involves breaking the sample into a manageable piece, mounting it in a resin to make polishing easier, grinding it to a smooth finish on the surface, and then polishing it to a mirror finish. This goal is to get a surface free from scratches and deformations that could obscure the view of the metal's true structure. The prepared sample is then examined under a microscope to identify any microstructures that might be present within it. For my analysis, fragments of these samples were mounted in resin. These resin mounts were polished in stages, starting at a coarse grit level of 320 and ending at a fine grit level of 1200, with silicon carbide paper for optical microscopy. Initially, an Olympus BX51 microscope, pictured on screen, was used to inspect the visual characteristics of the sample. After this, a scanning electron microscope was used to capture even higher resolution and more magnified images. After using the portable X-ray fluorescence, the samples were analyzed through X-ray microtomography. Drs. Kashuk Yanamandra, Ishan Ganju, and Nikesh Chalwa from Purdue University's School of Materials Engineering performed this analysis. X-ray commuted microtomography, also known as XCT, is an imaging technique that allows us to see inside the objects in 3D without cutting them open. The objects of interest are placed inside the micro-CT scanner. The scanner then rotates the objects 360 degrees while directing X-rays through it. As the object turns, detectors capture thousands of X-ray images or projections from all angles. The collected X-ray images are processed using sophisticated computer algorithms. This process reconstructs the 2D images into thin cross-sectional slices of the object, much like slicing a loaf of bread to see what's inside each piece. However, during the analysis, the slicing is entirely virtual and does not harm the object. These thin slices are then stacked together in the computer to form a detailed 3D model of the object's internal structure. This model can be rotated, zoomed in on, and explored in ways that would be impossible with traditional 2D X-ray images. XCT has not been previously applied to the analysis of metallurgical waste. Applications of this method evaluated the potential benefits of utilizing XCT, one of which being the ability to view the artifact's internal structure without destroying it. Since XCT allows for internal examination without cutting the object open, it is extremely useful for examining the internal structure of artifacts that cannot be destroyed or altered in any way. After completing portable X-ray fluorescence analysis, I was able to identify that most of the sampled waste artifacts fell into two categories. The first being artifacts with iron, cobalt, and calcium peaks with small amounts of other elements present, illustrated in the graph to the top right of the screen, which is for sample 1. And the second being artifacts with iron, cobalt, and calcium peaks with little to no other elements present or identified, represented in the graph on the bottom right of the screen for sample 4. The peaks represented in the graphs demonstrated the presence or absence of different elements within the sample. The height of the peak indicated that iron had the highest concentration out of all of the chemical elements present in the sample. All the samples contained a well-defined iron peak, which represents the level of iron present within the samples. The high iron level in these results, compared to the low presence of other metallic elements like copper, indicated that these indeed were associated with iron metalworking activities. Other elemental peaks identified by the PXRF included calcium, silicon, potassium, chlorine, cobalt, scandium, argon, titanium, and manganese. All samples in this analysis had iron, cobalt, and calcium peaks, but the sharp cobalt peaks identified by the PXRF results need further investigation, as cobalt concentrations calibrated by the PXRF are often inaccurate due to the similarity between iron and cobalt energy lines. Metallography of slag sample 4, seen on the right of your screen, examined the microscopic signatures of sample 4, which fell into the previously identified category of artifacts with a strong iron concentration and little to no other elements identified. And there we see the presence of metal microstructures that were identified. Visual analysis of the sampled artifact identified a large silica matrix with a sample containing wustite, a blob-like metallic structure in the glassy silica matrix pointed out by the red arrow. Wustite has been previously identified as a microstructure characteristic of iron metals. Sample 1 fell into the other category of artifacts identified the PXRF as having a high concentration of iron in addition to a mix of other elements identified above. Sample 1, depicted on the left of your screen, had no iron microstructures and appeared to be highly fired ceramic. Though this artifact may be related to metallurgical activity, as it possibly comes from the lining of the forge, it has been visually identified as a piece of ceramic. Images collected from X-ray computed microtomography analysis identified 3 different phases within the internal structure of sample 12, which can be seen in the image on the right of your screen. The bright white phases within the sample were identified as iron and had the highest density within the sample. The dark gray sections of the sample were determined to be silica, as X-ray tomography is able to more accurately capture the presence of silica within a sample in comparison to X-ray fluorescence. The internal structure also contained many pores aligned to one side of the sample and were represented near the surface. Cracks were also identified within the sample, moving from the exterior edge of the sample to the interior. One crack, circled in the image to the right of your screen, appeared to be filled with iron. Initial optical images of the slices recorded by the microtomography of sample 12 from Fort Ouiatenon depicted a cross-sectional view of pores and particles within the sample. This method allowed for us to see just how many pores were contained within the sample, likely connected to the heating process of the waste during forging. I'll now play a quick video of the collection of slices taken by the XCT to show the internal structure within the sample. An additional cross-sectional view of the smithing slag from Fort Ouiatenon provided a closer inspection of phases present within the sample. You can see the different shapes of pores within the sample, as well as a bright white phase identified as iron and a gray phase identified as part of the silica matrix. SEM imaging of the samples from Fort Ouiatenon identified both a fibrous and fern-like structure within the silica matrix, likely connected to the steps taken by the blacksmith during the forging process. This image shows an additional view of specifically the fibrous microstructure within the slag matrix in the smithing slag excavated from Fort Ouiatenon. Further research must be conducted in order to identify what actions taken during the blacksmithing process led to the presence of these microstructures. In addition, measurements of the distance between each of the fibrous structures could provide information on the rate of cooling of each of the samples, which will also help identify the actions taken during the metalworking process, as well as the rate of production from the forge. The primary metal identified by the PXRF was iron, demonstrating that these waste artifacts resulted from iron metalworking activities. Samples that did not have any metal microstructures present are highly fired ceramic fragments, possibly from the internal wall of the furnace within the forge area, or a crucible used to contain the metal within the furnace. Macroscopically, all of the selected samples visually appeared to be very similar. Microscopically, the samples presented metal microstructures within the silica matrix, like sample 4, are the debris that would have fallen off of a metal object as it was being worked by the forge. The XRF results from sample 1 fell into the second category of results, identified as artifacts with iron, cobalt, and calcium peaks, with a small amount of other elements present. Samples like sample 1 contained a large amount of silica crystals with no obvious metal microstructures. In contrast, these samples were originally called as slag and now were able to be identified as typical highly fired ceramics that were heated almost to the point of destruction, possibly from inside of the forge, but historical records have also indicated that the fort was set on fire at one point, which would also explain the remnants of highly fired ceramics. Given this pattern, the results indicated that around 10 of the sampled artifacts were highly fired ceramics, and 9 were likely to be from iron metalworking activities. The PXRF results fit well within the second category of artifacts identified, which leads us to believe that they were ceramics. The presence of calcium in these samples may indicate the use of charcoal as a fuel source during the heating activities, as the ash content of charcoal has high calcium levels. The varying levels of other chemical elements within the samples could also result from contamination within the forge. The pores identified in the samples through X-ray tomographic analysis may reflect bubbles formed because of the heating and cooling of metalworking waste. The microscopic structures identified during this analysis, as well as the further metallographic analysis via the scanning electron microscope, identified both a fibrous and a fern-like microstructure within the silica matrix, likely connected to the steps taken by the blacksmith during the forging process. This research serves as a preliminary analysis of the subset of the extensive collection of metallurgical waste excavated from Fort Ouiatenon. Chemical analysis of the waste artifacts using PXRF aligns with previous research describing the occupation of a blacksmith at the fort who primarily worked with iron. This research aligns well with historical narratives describing blacksmiths as an essential part of life within French forts due to their desirable skill set. I plan to further investigate the role of the blacksmith's labor in the production of metal goods used to further relationships between French colonists and indigenous peoples, as well as how this contributed to daily life at Fort Ouiatenon. I plan to examine both the production and maintenance of metal technology, including copper and copper-based metals, lead and iron, as a piece of a larger system of technological adaptation within the Midwest during the French fur trade. This research will continue to understand metal production and use within the Midwest during the 18th century, and I'll break this up into 3 different parts. One part of my research plan is to conduct a detailed review of historical documents, including merchant records from Montreal French fur traders, to learn more about how metal may have been coming into Fort Ouiatenon. Learning about what form metal may have entered the site in will help me understand what is represented within the Fort Ouiatenon collections. I've begun to establish connections with local blacksmithing hobbyists and historical reenactors through volunteering at the Feast of the Hunter's Moon and attending meetings of local blacksmithing clubs in Indiana. Plans for future research will include collaboration with historical reenactor blacksmiths at the Feast of the Hunter's Moon to examine waste produced from their activities to the waste collected from Fort Ouiatenon. With known metalworking practices, the results and analysis of reenactor blacksmithing waste may provide further information about what step in the blacksmithing process would lead to the development of microstructures, as well as the link to the presence and quantity of different chemical elements into different actions of the blacksmith or different workshop and furnace setups. Blacksmiths were crucial as the bridge between indigenous cultures and colonial cultures in the frontier through their navigation of trade networks and their role in the metals supply chain. Blacksmithing activities sat in the nexus of technology and cultural tradition through their technical practice and valuable skill set. The technological and functional aspects of the past metalworking activities at Fort Ouiatenon should continue to be situated within a broader socioeconomic context of the Midwest region during the 18th century. And I really want to thank Leslie, Rick, Kelly, Claire, and everyone at TCHA for granting me access to work with the collections and for enthusiastically supporting my work. I'd also like to thank the Department of Anthropology at Purdue, and more specifically my advisor, Corey Cooper, and my master's committee members, Ian Lindsay and Michelle Buzan, for their contributions and advisement of this work. I would also like to thank David Barr, Nakash Kalwa, Kashuk Yanamandra, and Nishan Ganju from Purdue University School for Materials Engineering for their support and contributions to this research. I would finally like to thank all of you, both in person and over Zoom, for attending this presentation and listening to me talk. So that is all I have for today. I'm happy to take any questions or hang out and answer anything. Check out the artifacts and whatnot as well. Yes.
Well, thank you for a fascinating talk. I really learned a lot, and you convinced me that blacksmiths were a really important link between indigenous people and European. My question has to do with one of the things that you did mention up there is, where does this metal come from?
Mhm.
You know, I mean, what's the local geology? Is there iron locally? Are there other elements? You want to look at copper and so forth. Is all that stuff being imported? I guess I'm really curious about the relationship between the worked metal that you are working with these slags and the question that you mentioned, where does this metal come? Where did it come from?
Yeah, so I know there was locally available iron in Indiana. I'm not quite sure if that's where this is coming from. If you have more advice.
There is bog iron reported in the mouth of Indian Creek
Mhm.
in the 1890s. Now, whether the mouth of Indian Creek is, you know, I'm sure it's moved, so I'm not.
Mhm.
I would assume it was most of it was brought in.
That's my understanding as well, that most of what the blacksmith was working with was brought in. But hopefully in future research, I'll take a look at exactly what was being brought in to then have a better idea of what the final products were and how that was contributing to the production of it at the fort and the remanufacturing of it. So stay tuned, I guess. Yeah.
So did you conclude that there was no evidence of smelting activity?
As of right now, yeah. I only did a really small portion of all of the artifacts in the collection, so I guess I can't say for sure, but out of everything I looked at, yeah. Yeah.
You mentioned that the pieces that you kind of determined were just high iron ceramics.
Mhm.
Was that found in the same area of the slag? So were they using the forge to fire ceramics? I guess I'm confused where the ceramics come in, if they were all found, all the byproducts were found in the same spot.
Yeah, so I think it was all come together. I guess the assumption that Dr. Cooper and I kind of running with right now, but can't be for sure, is that the lining of the forge. So when they're building the forge, it was that ceramic kind of lining. So that was assumably where I would think it was coming from. Because it also, because it also had a fairly high level of iron in it as well. So it had to do with metallurgical practices based on where it was found and that type of stuff. But I don't think it was possibly fired there, but it could be.
So I don't really know anything about any of this areas, so this was all new to me. It was really interesting. But I kind of was wondering if you could talk a little bit about what the implications are if you found smelting versus if you found forging only.
Mhm.
Like what does that like mean about like the importance of the fort, or like, you know, relationships with like among the people there?
Mhm. So I think smelting would be an entirely different like technical skill set that would be really interesting to look into more. In the literature reviews that I've done, I haven't seen a lot of smelting evidence being done at like French fur trading posts. So that would be a different level that I could examine and look at if there was evidence of smelting. So just kind of another avenue of technical tradition that would be really cool to look at. Also just the production too. So right now, I don't have a great idea of the scale of production, like the amount of stuff that the blacksmith was working with at any given time. So maybe that could identify things a little bit more in a different way, because the smelting of iron ore would be producing actual metal, which would be really interesting.
Yeah.
It sounds like the blacksmith was, if not formally, at least informally, top dog, very important person in the fort. Do we know what the populations were of people living at the fort throughout its history? Was it, we're talking 10 people, 100 people?
So I had one thing, I think it was 1740 something or 1726. There was about 20 French fur traders and then about 400 warriors that were in around the fort. So that's one number that I know off the top of my head. Others, I'm sure there are other historical documents that look
How
up
many
numbers,
fur
but
traders did you say?
there was 20 fur traders and their families from that quote, but I don't have the other numbers off the top of my head. I'm sorry. Yeah,
So a very interesting presentation.
thank you.
Once the British took possession in 1760,
Mhm.
were there specific implications for this?
For this research,
Well, by way of there being a changing in the guard, so to speak.
yeah, so and I think there also would have been another blacksmith that would have come in as well. I haven't investigated the difference of metal production when it was with the French occupation in comparison to the British occupation. I think that could be an interesting avenue of investigation.
No obvious French versus British.
Yeah, there was,
sides.
no, there was one report in the from Tordoff where she identified a separate like British kind of refuse area, which had some metal debris in it as well, so maybe there could have been more investigation there. I haven't looked at that part yet, but could be a cool place to look into next.
Was there a percentage of silver out?
Yeah, I haven't done.
Trade silver?
Yeah, there's other trade silver. There's some examples over there. I haven't looked at the trade silver. But I think that could be a cool avenue as well. So, yeah. Yes,
Thank you for the talk.
thank you for coming.
What I was thinking with the blacksmithing, when I think of blacksmithing and in your photos as well, from Colonial Williamsburg, they have the like stereotypical anvil, you know, that falls on the cartoon character's head.
Mhm.
Would you find something like that at a Fort Ouiatenon, something so diagnostic? At like a similar site, maybe in the Midwest, that you could say, besides just slag, that there's also this these diagnostic artifacts that might indicate blacksmithing, or is it would there not be something so like easy to identify at a site like that?
I'm sure there could be. I don't think there's an anvil in the collections here. That's not. I don't know for sure. I think the anvils were probably one really heavy and two very valuable because they're a nice chunk of metal. So they wouldn't want to leave something like that behind if they could take it. But I think that would be cool to look at some diagnostic activity to understand it better. I can investigate that more as I continue further along in this journey. Yes.
Sorry, just kind of off of that, and you might already have said it, I apologize, I don't know a whole lot about Fort Ouiatenon, so I learned a lot today. But so why exactly was Fort Ouiatenon, like, why did blacksmithing stop? I guess at Fort Ouiatenon, I guess it's not happening right now anymore.
So the fort changed hands to the British and then changed hands again and then was burned
Oh,
down. Yeah, so it was burned down.
the wrong kind of fire.
Yeah. So that's why, I presume. So when the occupation ended.
Oh, okay. Who burned it down? I'm sorry.
Americans? I don't know.
Okay, interesting.
Don't know.
That was like Kentucky militia, I think, in the 1790s. By
Oh.
that point, supposedly,
Was mad Anthony.
there were still people living there, but it seems like descriptions of the fort, it was not really functioning as a fur trade fort by the
No,
1790s.
No, but it was burned down by the US Army.
Oh.
To
Oh,
prevent
okay.
the British from reacquiring
Oh,
the
okay.
fort,
I see.
since we were
Like
still.
post-Revolutionary
Yeah,
War. before
Right,
everything
because we
was-
were still actively engaged with the
Right.
British in Canada.
So there-
And the French pretty much, the French pretty much cleared out in 1780s. I mean, there was a lot of, bad relations going on, and they either went up to Keith Tippecanook
Hmm.
or further north or down to Vincennes.
And they took the blacksmith.
And they took everything with them.
Yeah.
Interesting.
Valuable tools.
Okay, so no animals.
Because out here in the wilderness, animals are not readily.
Right.
So,
Left behind.
Well, it's interesting to think about who the blacksmiths were, like how many were there and where did they come from? From Montreal or Europe, and like research I've been involved with the fur trade in Alaska. There were entire, class, that the Russians actually borrowed the Spanish term Creole, and they used that term for all people who were descended from unions of Russian fur trade employees and various Alaskan Natives women. And those individuals had particular rights that Native people did not have within this context. Some were sent back to Russia, educated, and then would work for the fur trade companies. So there's a site I worked at where supposedly some of the workers involved with metallurgy or other crafts were actually Creole or possibly Alaskan Native. I don't know. I've yet to see any discussion of that regarding Métis peoples taking on those kinds of roles in the French fur trade, but I don't know if maybe it's out there somewhere.
And that was, a blacksmith was one of the things that the native population in this area absolutely demanded.
Yeah.
They would come here because of repairing firearms and what have you.
Mhm. Yeah. Definitely. Good. All right. Thank you so much, everyone.